Okay, well, we're solidly on the hour now, so it's my very great pleasure to introduce Nick Shea to give our final talk of this workshop. Nicholas Shea is Professor of Philosophy at the Institute of Philosophy, University of London, and an Associate Member of the Faculty of Philosophy at the University of Oxford, as well as author of the recent book, Representation in Cognitive Science. He is an interdisciplinary philosopher of mind and of psychology, cognitive neuroscience, and cognitive science. He went into philosophy after a brief career as an intellectual property barrister, following a degree in mathematics at Oxford. He completed his MA at Birkbeck and PhD at King's College London, and then worked as postdoctoral and then senior research fellow at Oxford before returning to London, firstly at King's and then at the Institute of Philosophy, as well as philosophical work on mental representations, inheritance systems, consciousness, and the metaphysics of mind. He's published in scientific journals in collaboration with psychologists, cognitive science, neuroscientists, and biologists. And today he's going to be talking to us about content-specific computation in artificial neural networks. Over to you, Nick.
Thanks, Henry. Let me just talk a bit and you can check that my audio is all right and you're seeing the slides. Okay, good. Well, it's very nice to be part of this this workshop and to have a connection with the project. This Kinds of Intelligence project has so much interesting work coming out of it over the last few years, and all these very interesting events. I was sorry I wasn't able to get to that fantastic festival of almost everyone involved in the cognitive science or philosophy of intelligence a few years ago in Cambridge, so it's great to be able to take part. So I want to talk about something that's an issue within deep neural networks, which I think has got wider importance. So as everyone here will be familiar with, I think there was an absolute explosion in the capacities of neural networks, the old style term connectionist systems, in 2012 when they started to be very good at visual categorization tasks, and it's since been shown that the same basic architecture is very good at learning one kind of task after another. But there are some limitations, and they go to this issue that's shown up already in this workshop of what style of intelligence are these systems using, and does that interact with the way that they have limitations. So there was an older debate in philosophy about this connectionist or neural network style of computation, where, for example, Jerry Fodor and Paul Smolensky were advocates of two different poles that argued that there was a deep limitation in the kind of computations performed by neural networks, in that the structure of their representations didn't involve compositionality. So there was some limitation inherent in the way that the representations are structured that get transformed in their computations. And I think that is an important difference, but today I want to focus on something different, which is something about the nature of their computations, the transformations between representations. I'm going to argue that the basic deep neural network uses a computational style, which, although very powerful, has limitations, and that there are benefits to be harvested from a hybrid between that and another computational style, which is much closer to the computational style of good old-fashioned AI or the serial computers that you and I are using now to interact. So the plan is I'm going to say something about this computational style, which I'll characterize informally just as dispositional computation, because it arises from building in, training in dispositions into these networks, and then I'm going to come back and try and characterize it, this style more precisely. And the term I'm going to use for the precise characterization is content-specific computation. Then I want to turn to an example system, a neural network that has been trained to overcome some of these limitations by using what they call episodic memories. They're kind of episodic-like, they're not quite like human episodic memory. And I'm trying to drill down into the way that add-on works. And it speaks to a much older issue where Randy Ganastel has long argued that there's a limitation in the computational style of neural networks and of neural processing in cognitive neuroscience as we understand it, which is that it doesn't make a separation between memory and computation. So I want to look into that argument from Ganastel. And then from the interaction of those two things, I'm going to bring out this claim that I'm going to make about the nature of the basic computational style of deep neural networks, which is that the computations are content specific in a form I'll try and spell out, contrast that with the kind of more general computation. That doesn't necessarily mean it's generally more capable, that the computational principles are more general. that we're familiar with from logical reasoning or from classical computation, which is the non-content specific. And that's the thing that you find in this hybrid that I'll tell you about. And finally, I want to say how this distinction relates to some other distinctions that have been made in the literature. So that's the plan. I should say that most of what I'll say today is already out in a paper that recently came out in Minor Language, which Henry and Ali asked me to speak to. So the references there, and there's also I'm also very grateful to all the people I named there who've given me lots of input on this over the years. I mean, well, over the months I've been working on it, but I've not given up working on these issues. So I'm very interested to hear people's feedback today, and I'm sure that will feed into future things that I'm thinking about on this project. Okay, let me start by looking at deep neural networks. So the basic principle of these deep neural networks is there's a set of artificial neurons or units that are connected in layers by weights. So at the top you have a picture of one of these kinds of architectures, lots and lots of units at the different layers, and they're all notionally interconnected with one another, and activation flows forward based on weights on those connections between layers. Successes in the early networks were the early new wave networks were in image classification. So for example, a network will be trained up on tens of thousands of image examples where it's supervised, it's told what those images should be classified as. And then the output is a weighted vector, or kind of weighted estimate of what the right label for those images are. And so this would be like some images that you might give it in a training set, and these are the kind of outputs you'd get. It sees a picture like this after training, where it's new, and it weights the label might as the most likely way of classifying that. And here's some weights on some other things it would label it as. This thing gets labeled as a container ship. Are you seeing my cursor? Am I gesturing in a way that makes sense? Give me a nod. There's a cursor moving. Yeah, okay. And then for some of them you get more than one weight, so you get agaric and mushroom here. So that is trained on this kind of task, and what's happening is that it's presented with a huge amount of data and many, many episodes, where on each episode of presentation, the weights in the whole system are slightly tweaked to bring the output slightly closer to the right answer. So that eventually, when it's been trained on these images many, many, many times, it produces the right answer for all of them. And the clever and surprising thing is that it then generalizes to new instances of the kind of images it's been trained on. Wow, entirely new images can fit into the right categories. So in this system, computation and memory are combined. The way that it remembers the past is by setting up dispositions to move from inputs to outputs that remember the kinds of moves it's been trained to produce. So it's trained on a whole series of different input-output mappings. And what it has to do to one region of input space, one image or small collection of images, say the ones that are dogs, is quite different from what it needs to do to the ones that are container ships or cherries or convertible cars. So it's got to be trained up to exhibit all these different dispositions at once to transform inputs to outputs in an appropriate way. And that's quite different from transforming all regions of input space according to a common principle. The big discovery is that you can get something that will produce all these dispositions at once, because you think that there's an immediate problem, that the way that you train it up to respond correctly to dogs or maybe to animals is going to interfere with the way that it needs to respond to artifacts or vehicles. But it turns out it is possible to get it to implement all of these at once, and also that given enough data and enough parameters, it'll do that in a way that'll transfer to new images. And it's not just that; also the way that it works depends on the architecture that you set up and the training regime. So clever things in training like regularization or training some layers before others. So there's quite a lot of tweaking and hand design of architectural features that allow these things to work, but it's still impressive and surprising that they work as well as they do. So of course, at the level of the node level implementation, they are using very general algorithms. So there's a general algorithm for learning that uses back propagation of error to tweak the weights a little bit on each occasion. The thing that I'm going to argue is content specific is at the level of the distributed patterns of activation, the transformations you get from one distributed pattern of activation to another. So these have turned out to be a good model of various tasks that humans perform in a rapid, domain-specific way. But this is some pictures extracted from work that compares the way that a convolutional neural network doing image classification processes information, and compares that to processing in the brain. And it turns out that there are pretty striking similarities between layer by layer processing in the trained network and layer by layer processing in the brain. And these images give you a sense of why that should be. So the network has many layers. We're looking at the early layers, and at B, you can see that the receptive fields for the neurons become wider as you get deeper in the hierarchy. And at C, there's a reconstruction of which kind of features the neurons are specialized for. And this is they call it a visualization. It's not a kind of direct reading. It's itself a statistical reconstruction of what the network's doing. But I think it is a valid way of looking at the kind of specializations you get. And you can see in early areas there on the left, under C, you get specialization for contrast and contrast boundaries. And then you get things that are more like textures. And then those are transformed into ways of picking out particular features. And those features can get gradually put together into particular categories of objects. So the transformation, that's a bit like what goes on in the visual system, and it picks out certain kinds of features and then combines them in a weighted way to get to other kinds of features. So these are, I've said these have proved very successful, and I've tried to bring out the way in which there's something that's kind of dispositional about the way they work. And a consequence of that is that they require this extremely extensive training, and they're relatively inflexible when you try and extend it to new cases. Because what you've trained in, I mean, just this is a very simple picture, but because what you were trained in is it to do this whole bunch of dispositions at once by cycling through instances of all of them, getting it to maximize all of them at once. If you say, right, now I want you to perform another disposition, I5 to 04, say, then there's a risk that getting it to do that is going to undermine the information that's about the past that's stored in its dispositions for all the others. You can get it to new things, but you have to keep introducing the old things as well to stop that. So the term that's used for that in the literature is catastrophic forgetting. There's a risk that if you try and get it to do something new or transfer to a new realm, and then you do some retraining, it'll catastrophically forget all the stuff that's been so laboriously learned in the past. So in the face of these kinds of limitations, there's lots of different groups working on lots of different add-ons and tweaks that improves the capacities of these systems, and it's, you know, the literature that's changing incredibly quickly. I want to just describe two of the additions because they give us a contrast that's quite useful for bringing up my point. And these are ones that Matthew Botvinnik and colleagues draw out in a recent review paper. The first way of overcoming these limitations is to train the system on a series of different but related problems and get it to solve them all at once, where each problem itself involves learning. So this is done in a context where what the system has to do is reinforcement learning. So it has to learn which stimuli and which actions in which context will produce rewards for which stimuli. And a solution that Botvinnik himself has pioneered in some of his work is a system that can do what he calls meta reinforcement learning. So you train it on a whole bunch of related reinforcement learning problems, but although the structure of the problems is roughly similar, what changes is in one problem, certain stimuli will be rewarded, and then the probabilities change and different stimuli will be rewarded through different actions. And you find that you can get a network that can relearn what's rewarding without having to change the weights. So after enough training on enough different problems, you give it a new problem, and which is about learning which actions are rewarded for which stimuli, and it can, after a series of presentations of those stimuli, can learn to do the right thing, but without changing its weights, but just by taking the feedback on previous actions as further input. So it has kind of trajectory through activation space that ends up finding a solution. And that's a way of having a kind of memory, but it's a kind of dispositional memory. The whole thing has a disposition to respond to short trains of input with the right kind of output. And they contrast, what Vinnick and colleagues contrast that with a different kind of solution, which is to store explicit, what they call episodic memory. So of the episodes, training episodes that the system's encountered, it'll store those and their outcomes explicitly, and then compute with those explicit memories. And that's a very different way of solving this task of dealing with the past. So I want to dwell on that a little bit to show you how that works. So here's a picture of an architecture that does that kind of computation with explicit memories. This is the differentiable neural computer architecture taken from a paper by Graves and colleagues in 2016. And the way that this works is by, for every training episode you encounter, storing the state that you were in, the action you performed in that state, and then the long run reward that you encountered. So not just any reward that you got immediately when you perform the action, but after several trials, what reward did you get? In principle, after all the future trials, what reward do you get, but in a way that the future is discounted. So it's like a future discounted weighted reward for every action and every state. The system is presented with some state, does some action, gets some reward, and then goes through a series of states, and for each state it has a memory store that stores the long run reward for that state. And so this memory store gets longer and longer as it encounters more and more samples. So that's called a non-parametric form of memory. The number of parameters you need to store the data you encounter isn't fixed in advance. You need more parameters for each new episode that you're trained on. Then what it does in order to calculate what to do is it encounters a new state, and then that's this new state, and then it calculates how similar that is to every state that it stored, and then based on those similarities, it works out an estimated long-run value for that new state. So if this new state is unlike most states it's stored, but very like this state, then that'll get the highest weight, and it'll think, I'm going to get the same reward in this new state as I got in this state. And you don't have action in this picture, but if the reward's contingent on action, that'll tell you which action to perform to maximize that state, that long run reward from that state. So this system, so I was talking about the dispositional learning that involved cycling through lots and lots of samples and gradually tweaking behavior to perform the right thing. This way of storing the past does in principle allow it to learn in one shot what to do, because it can encounter an entirely new state, do something and get a reward. If that's a high reward and then it encounters that state again, this weighted sum of similarity will just say, we've got the same state again. This is what to do to get a reward. So unlike the dispositional, basically the dispositional principle, this can do a kind of one-shot learning. Now, this particular model is actually not in that widespread use, but it exemplifies the point quite nicely, although related things are. This on its own doesn't scale very well to very high dimensional problems, although you can add in various kinds of sparsification that help. But it does bring out this way that adding in explicit memory allows you to overcome just like stamping in a bunch of dispositions in order to get the system to perform the tasks you want it to perform. There are other ways of doing that. So there are some quite well-known systems that bolt on a form of relatively general reasoning, or bolt on computing with a model of the problem, model-based reasoning. So the Google DeepMind group in London famously produced a computer that could beat the world champion at Go, the ancient game of Go. And that used these deep neural network methods to analyze patterns and to learn rewards, but it also had a model of the game, was also told what the game space was like and how moves would change you from one game space to another. And it calculated forward using that, using a computational model of the game space to work out what's likely to happen next, or all the possibilities for happening next from every state. So that's another kind of hybrid. So there are other kinds of hybrids, but I want to focus on this. There are other kinds of hybrids that use the principle I'm going to eventually land on, but I want to focus on this episodic memory system as a way of bringing it. The final thing I want to highlight before I move on from this example is that there's a computational cost for storing these, which is more parameters, but of course deep neural networks have loads of parameters, but there's a computational cost for computing with these, because as you get more elements in the memory store, the computation of similarity that allows you to compute what to do in a new state becomes longer and longer. You've got to take the new state and multiply it by all the existing states, and once you have a large store of memory, that becomes a very computation heavy process. So we can see something here that may be a bit familiar. So the basic dispositional model is very, very learning heavy, but it can compute what to do very quickly because you just stamped in a disposition. This model slightly has a way of transcending the inflexibility of those basically dispositional models, but at a computational cost. At decision time, when you're given a new stimulus, the computation of what to do can become extremely onerous. And I think that's for a reason that's related to the distinction I'm going to get to. Okay, so now I want to move on to a much older argument that Randy Gellerfeld has been pushing for a long time about limitations of neural networks, and he also thinks of the limitation of our understanding of how the brain computes, and that's the importance of memory. So this relates to what's going on in these DNC systems that add an explicit memory. So he's argued this in many places, and probably at greatest length in a book with Gellerfeld and King called Memory in the Computational Brain. The argument is that there's a basic limitation for systems that don't separate out memory and computation. And as I've been describing the kind of unsupplemented setup of a deep neural network, the way it's so good is because it learns from the past by changing its computational dispositions rather than by having explicit memories. And he's got two arguments. One is a kind of abstract computational argument about the limitations of what a finite state autonomous can do. That doesn't apply directly to these cases because it turns on issues about what it is to implement a computation in a way that I think makes it difficult to read as a direct argument about whether neural networks have memory in the right sense, because they do have memory in some sense. So the abstract computational argument is that you need memory in order to transcend the limits of what a finite state automaton can do, where both of those things are defined in kind of abstract computation space. But it doesn't yet show that deep neural networks lack memory in the sense that would transcend that argument. But he has another pragmatic kind of implementational argument, which I think is much more direct. He says, look, if we look at the long history of computing since computing machines were first developed, all the ones that have done anything any good, that have been practical, have had a deep-seated distinction between computation and memory. And there's some practical reasons for that. Now, of course, that's not quite true since 2012, because we've got these systems which are also very good at some things that don't have that distinction. But I think it's interesting to draw out what Gellerfeld says is the source of those limitations. And the source is the problems with dedicating computational machinery to dealing with the past or dealing with long-chain input. So take a problem where what to do now depends not just on what you've just been presented with, but with something in the long-distance path. So maybe you're out foraging, and whether to turn left or right now in this kind of foraging environment depends on something you observed yesterday. So yesterday you observed a tree that was about to come into fruit, or you observed a place that's barren, so you need to avoid. So to do the right thing now, you have to take into account that past state, and it can be quite a long time ago. One way of doing that is to have these inbuilt dispositions to produce outputs for long chains of input. So there's two different long chains of input that go right from yesterday till now. One includes the fruiting tree, and another tree includes the tree that doesn't have any fruit, and the rest of the intermediates are the same, and the output you should produce needs to be different. But if we're going to do that in the dispositional way, Galastel and King argue, we've got to dedicate computational resources, kind of a fixed disposition, to each of these long chains of input. And as you have to deal with more and more distance passed, more and more resources have to be dedicated to dealing with the many different possible inputs, because the possibilities are exponential in the length of the input. They have the term the infinitude of the possible, which is not quite right, but there's a kind of exponentialness of the possible that you deal with. And as they argue, a machine that writes to an explicit read-write memory, a bit like the DNC that we just saw, sidesteps that computation, that kind of combinatorial explosion by storing explicit memory and then only computing with it when you need it subsequently. So I think we can see the two ways of dealing with the past. Okay, and then and classical computers then have a way of computing with those explicit memories, but which raises familiar problems in its own right, that you have to have some way of identifying what the relevant memories are to compute with. So that's one aspect of what's often called the frame problem. So in the two different solutions that Vinnick review offered to the limitations of deep neural networks, I think we can see both of these things at work. So I mentioned meta reinforcement learning, the idea of training the system on a bunch of different problems so that in its dispositions, without changing weights, it can do the right things in response to chains of input. It can do kind of learning on chains of input. So I think that exemplifies this solution, where you've trained it so that it can deal with quite long chains of inputs and produce different outputs with respect to them. But the episodic deep reinforcement learning system deals with it in quite a different way, with these explicit memories in the way that Galastel and King argue. We need to, certainly in the way that's been so powerful in the history of practical computing machines, like the ones you and I are using now, to communicate with. Okay, so I hope that does enough to motivate the idea that there's a relatively deep limitation and deep distinction around computing in the purely dispositional way versus storing explicit memories and being able to compute with those, although computing with the explicit memories raises computational problems in its own right. Now I want to drill down into that distinction. I'm going to argue that to make good use of those explicit memories in the way that this system does depends on computing with them in a different way, computing with them in a kind of general way. So we can see that in this computation. So the computation here of similarity of the new state to all the different stored states. That's not specific computation that depends on what that's about. It's one that just applies in exactly the same way to all these different stored states, this kind of vector comparison here. So you can deal with this potentially indefinitely extensible store by having learned or set in advance a computation that's going to apply in the same way to all of them. And that's very different from the stamped in dispositions of the basic neural network. And it's that distinction I want to drill down into. So in the Graves and colleagues paper, this is what they say about the distinction. They say what the explicit memory system does is to deploy an algorithm that's independent of the particular values of task variables. So this is a distinction that's often drawn as a way of characterizing how classical computers work, which is that they use variables rather than using specific content and states. And I think this is closely related, but distinction, I think, is not quite the one of using variables, because I think you can carry out these general purpose kinds of computations on things that aren't actually variables. As we see in this case, you're performing a computation on something that's not a variable, it's a kind of filled in state, but you're still performing a general computation, the same computation on all of them. So I want a distinction that's related to that, but slightly more general. So take this bit of inference that we could use in reasoning and that you can implement in the computer. You can perform this bit of reasoning: all sparrows fly, Abe's a sparrow, therefore Abe flies. That's a perfectly general pattern of inference, but if I've invited you to do it in your mind, then you performed it on, not on variables, but on contentful representations. You performed it on representation of a particular sparrow and the representation of a particular property being a sparrow. So that it exemplifies the kind of generality we're talking about, but it's not taking place over variables. Contrast this bit of reasoning where you can manipulate a mathematical formula that involves variables and rearrange it to reach some conclusion. This really does involve variables. Both of them are general. They use a pattern of reasoning that doesn't depend on what the particular values are here. And this pattern of reasoning doesn't depend on what the particular values are here. But this one doesn't involve variables. So I think the distinction is slightly deeper. And we can see that going on with relational reasoning, for example. So you could do some reasoning involving a family tree. Here's a family tree involving a bunch of people. I have no idea who any of them are. And you can work out relations between them using the tree to stand in for genealogical descent. So you can work out that this person is 2 generations after this person and this person. You can work out how many grandparents this person has got, and you could then eventually work out if they've got people in parents or ancestors in common. That kind of reasoning doesn't depend on who the particular people are that are pictured here. It's going to work whatever the people are. But in this representation, we're not using variables, we are using specific representations of people. But the form of processing that I'm doing over them is not specific to the content of the particular people. It is specific to the content of the relation. So the relation stands for genealogical descent. It's not like it could stand for any old relation, and the reasoning would still work as well. We can generalize because we can use this as an analogy. So we can use the genealogical tree between people as an analogy for other areas that have the same kind of structure. Darwin famously did this in understanding how species diversify. So he drew a tree in his notebook and had species diversifying from each other. But even there's a constraint on what the relations in the tree could stand for. So this is a kind of computation that's not at all content specific as to the individuals, but has got some content restrictions as to what the relations stand for, given the way that you compute with them. Okay, so now I want to get to the really philosophical meat, which is to be able to define this distinction more carefully. And to do that, I want to back up and just lay on the table a notion that's central to the representational theory of mind. So all of this is taking place within the representational theory of the mind, the idea that we can explain behavior and cognitive processing transitions in thought in terms of the processing of representations, where representations are actual physical vehicles. They're things that get manipulated, and since they're actual physical vehicles, we can describe those manipulations in non-semantic, non-meaningful terms. That's the commitment, that there's some non-semantic causal basis for the transitions between representations. Why is it useful to transform representations? Well, because you set things up through one process or another so that transitions between representations are faithful in some way to the contents being transformed. And here's a very basic way of being faithful. I've shown you it already. If you set up a system so that it's got dispositions to move between premises in this kind of form, the conclusions in this kind of form, then that's very useful, because if the premises are true, the conclusion is bound to be. So that's having that kind of inferential disposition is a way of moving from true premises to true conclusions. That's a useful kind of disposition to have. So I think this notion of being faithful to content is actually quite an inclusive one. We can apply it to practical inference, where you've got desires or intentions. I think we can apply it to transitions between contentful and non-contentful states, and between conceptual and non-conceptual states. It may even be applicable to transitions between contentful states and affective states. But in the things I'm talking about today, we're talking about transitions between states that have descriptive kind of content. So the notion of faithfulness now will be just kind of content preserving, roughly truth preserving, but not truth preserving in the strong way that we see with deductive inferences, where the conclusion is bound to be true if the premises are necessary truth preservation. But the slightly looser sense that the conclusion is likely to be true if the premises are true, or the outputs are likely to be true, the inputs are true. Because for a practical machine, that's good enough. Having something, if you can set things up so that the outputs are likely to be true, given the truth of the inputs in the kind of environments you're working in, that's a very, very useful system. So that's the notion of faithfulness to content that we need to get the usefulness of these representation processing systems off the ground. Okay, so now I want to characterize this special way of computing that the DNC system was exemplifying when it computes with its episodic memory, and which is like the general purpose reasoning we see with logical reasoning here. It's slightly complicated because I think the best way of characterizing the case is by reference to the negative case. So I'm going to give a positive characterization of something that I define negatively as non-content specific computation. So there's a lot of negatives floating around, but I think actually this is the clearest way of homing in on what the thing is. So remember the idea, which is that the disposition engine ends up having stamped into it some quite content-specific transitions. So picture those as going on within domain-specific systems. So you may have an expectation built into your visuo-tactile systems that when you see something like that, it's going to have the texture of these kinds of things coming off it. I mean, I can almost get the feeling in my nose of that kind of feeling you get off dogs just by looking at a picture in a dog. So it's got all kinds of domain-specific expectations built into, through training, through experience, into the computational dispositions you make in these kind of sensory motor systems. I think there are also these kind of transitions as you move from conceptual thought into visualizations, or as you categorize what you see or what you experience. So those are the contrast class, the thing that I'm going to define our special kind of computation by contrast with. But these still meet the representational theory of mind desideratum that given correct inputs, the outputs are likely to be correct. So this is a way of meeting that desideratum. But logical inferences meet it in a different way, and I'm not just talking about deductive logical inferences, so I'm going to talk about a slightly broader category, where the category is transitions that kind of depend on the broader pattern, not on what the specific representations being used are. So to do that, I'm going to define what I'm going to call a broadly logical concept first. So that's a concept on the content of which the validity or truth conduciveness of a formal pattern of inference depends. So I'm just pushing back the problem. Now we've got the notion of a formal pattern of inference, and that's the idea of a very generally applicable pattern of inference. Let me give you some examples. So the kind of examples I'm starting with, deductive ones. If you're so wired so as to produce this kind of transition, then things aren't going to go wrong. And this is going to work no matter what proposition size, thoughts, or sentences you put in here. Similarly, for using if-then, that works for any singular terms and predicates that you can put in here. So these are very general patterns, but general patterns of inference needn't be deductively valid. Here's some kinds of reasoning that we probably go in for. We draw conclusions from statistical premises. We get some evidence that something's very likely to be true, and then we just conclude that it's true, or form the belief, or we reason as if it's true. And similarly, we generalize from observation. We observe lots and lots of things that are F being G, and then we are disposed to infer from observing a new thing, A being F, that it's likely to be, that it is G. So these patterns are also kind of useful patterns to go in for. They won't go wrong very often, but they are slightly more specific. These kind of probability projections depend a bit on which kinds of thoughts you put in here, and these kinds of projections famously depend on using the kind of predicates that we all use, projectable predicates, although that doesn't really characterize them, other than the ones who work for this, but they work very generally, but not quite as generally as these. So the usefulness, the faithfulness to content of these transitions does depend on content. It depends on content of their kind of logically terms, like all and if then, probable, observed. It doesn't depend on the content of the open class terms. And that's the contrast I want to draw. So what makes something non-content specific is that it depends only on the content of these broadly logical concepts. What are the broadly logical concepts? They're the ones that figure in formal patterns of inference. What are the formal patterns of inference? They're the very general ones. So we've got a little local holism approaches here, but I think it gets our definition off the ground. So now I'll give you the definition. Content-specific transitions are transitions between representations such that whether or not the transition is faithful to content depends on the content of representations other than broadly logical concepts. And I told you there were all the negatives because the non-content specific is just the negation of that. And that's negation of something that already contains a negation. But I hope that by just giving you the examples, you can see what I'm getting at. And I think this way of thinking about gives us a formal way of capturing that. So let me bring that alive a bit with an application back to deep neural networks. So there's relatively little work. There's a huge amount of work on making these things perform tasks, do incredibly clever things. There's relatively little work on how they work on AI interpretability. But some of it begins to get at this issue. And so I'm going to refer to just this one distilled paper by Chris Olah and colleagues, all from the OpenAI group, where they're interested in this question: how do our convolutional neural networks doing image processing, how do they work? And here they're focusing on what single units do, what single neurons do, which I think is a slightly artificial abstraction, but maybe one that we need in order to get this off the ground. So I've argued in old work that the transformations that are computationally important are likely to be between regions of state space rather than from neurons to neurons. And there's a bunch of more recent work on that notion, how we should understand that notion. So Cameron Buckner has got published work and forthcoming work on that. And I know you people in Cambridge may know Firaz Azhar, who has a particular proposal as to how we should individuate these regions in terms of planes, intersecting hyperplanes. Other people do it. Buckner does it in terms of manifolds. In any event, I think we need to generalize away from individual units. So Olah and colleagues say they could be thinking of directions in state space as well. But I think just looking at units, they are able to do an analysis, which I think illustrates the distinction on that. And this, I'm giving you this slide to show you that the things that are being represented needn't be ones that we're already familiar with. So I showed you earlier on that there's this interesting work showing that there's similarities between visual processing of these kinds of networks and visual processing in the brain, where features like contrast boundaries and edges and textures get represented. But looking at how these systems work, looks like we can discover that there are other things that are useful to represent in order to solve this problem of categorizing objects. And these are a set of units that represent boundaries between high frequency visual areas and low frequency visual areas. So again, these are kind of reconstructions. These are telling you what the preferred roughly what the preferred stimulus for this unit is. But you can see this collection of units are finding places where there's a boundary between an area of high visual frequency, and an area of low visual frequency at different orientations. No one was particularly expecting to find that, but now that we've found it, you can see why that might be a useful way of useful intermediate categorization, because a lot of the things that the objects they're trained on, the object itself is high frequency and the background has got lower frequency. So this is a cue to where the boundary between the object you need to categorize is and the background. That may be generally true in the specifics of our visual environment, but it's especially true when you're training on images, which tend to be photographs that have been focused on the object. So this is a kind of good feature to get onto. So that's an example of kind of a computationally useful feature. Now I want to give you an example of computationally useful transformations, and actually they don't do it with this feature, but they do it with another feature, which is a way of detecting dogs. They find that there seems to be a specific neuron for detecting dog heads, no matter what their orientation is. This is a kind of picture here as to what its preferred stimuli are. So dog heads in lots of positions under lots of orientations. These are the kinds of samples that it was trained on. I'm showing you this because they tell you something about what the likely computational steps are. So this is over 4 layers. This is a kind of picture of the kind of computational steps that's performed. It has a neuron or small set of neurons that are good for identifying left-oriented dog kind of features, not just facial features, but like textures and so on, textures and features, and another for right-orientated ones. And they get combined in a kind of competitive pathway, forcing the right against the left in such a way that you get neurons that are good for detecting oriented heads. So I'm looking to the left here because my second screen is to the left. So I hope that's not too distracting. And then those get weighted in a competitive way, in a way that can also bring in neck information, but it's not looking very dog-like yet. But then by combining the left and right cases, you end up with something that's more like the invariant head representation that we eventually get at the 4th layer. And then you combine that with neck information to get something that's close to what they actually find. So these are just at single unit levels. This is kind of a rough idea of the computation. I don't think this is actually getting onto the real computational story. As you can see, it's all quite messy. But the thing I want to bring out is that this plausible move in the direction of a computational story is content specific, right? These are useful transformations to make in the realm of dogs or maybe furry animals, but not ones that are going to work across the domain of everything. And similarly, these kinds of features, they're a good way of detecting the edges of objects in our statistical environment, or maybe even just in the statistical environment of photographs that this thing was trained on. So I think, I argued at the outset that deep neural networks in their basic configuration are stamped in, trained to have a set of input-output dispositions. That doesn't yet tell you how the internal steps are working. But I think this kind of work shows that in order to get these parallel set of very different input-output dispositions, the internal steps are also often content specific. They often do things that work in a particular domain. Quite different from the non-content specific computation that we saw with the DMC, when it has this extensible store of explicit memories and has to compute the same thing with respect to each of them. Okay. So that's the distinction, that's the main meat, that's the distinction I wanted. And I think this distinction can do some work in relation to broader questions, like the question that came up this morning of what do we need in order to characterize what's general about the generality of human intelligence, or generality of what an artificial general intelligence is like. There's a paper in Behavioral and Brain Sciences with Penn and colleagues, where they argue that something very like this is what's distinctive of human cognition by comparison to cognition of other animals. That humans are able to do what they call role filler independent reasoning, which is closely related to the non-content specific reasoning that I'm talking about. And there the key innovation is being able to perform some procedure which is independent of the value of inputs, which is quite different from the disposition engine in the basic work. Okay, now I'm just going to check in with Henry about time. I've given you the basic distinction and the motivation for it. I can say a few more things, or I can stop there for a pause and questions. Would you like 5 more minutes, or should I stop?
I think another 5 minutes is absolutely great to explore some of the more the implications, and yeah, I think that'd be great. Okay, so okay, what I want to argue now, which I think illustrates a bit how this distinction works, is that the human conceptual reasoning system goes in for both kinds of transition. So here's a way that we
might reason with concepts. We form some concepts that are verbally expressive, some conceptual thoughts that are verbally expressible. And then we can go through, we can use our domain-specific resources, for example, in perceptual imagery, and then we can draw conclusions that are, again, expressible in concepts. So here by concepts, I mean devices of categorization or generalization that are sub-propositional, so they don't make a claim on their own, and that figure in our deliberate explicit reasoning, even if they figure in other things too. One of the things that's distinctive about our conceptual thinking is that it can figure in transitions of, I think, of both kinds. So transitions from concepts to sensory representations and categorization. So when we see something and we apply we see some hair here, we apply the concept of hair to it. Those are both content-specific transitions. And that's not a general way of working. That's something that works from this pattern of visual input to this concept. And similarly, when we exercise the concept dog and we visualize these kinds of things, that's a content-specific transition. And of course, I've argued already that within domain-specific systems, you get content-specific transitions. But the kind of logical inferences that we started with, those are non-content specific. I switched to Socrates here just because it's the classic philosophical case rather than Abe and sparrows. But again, it fits a pattern that will work whatever the contents involved are. And this is a pattern transition that I think human reasoning almost certainly goes in for. There's a third pattern, which I think is also a characteristic of human reasoning, which is to make content-specific transitions that don't go via non-conceptual resources or domain-specific resources, that work between conceptual representations directly. So you kind of have wired into your concept-based thought certain expectations. So, for example, on encountering something that's a dog, you have an expectation that it's going to bark, or you might have wired in generic kind of expectations like whales are mammals. Actually, that's a universal generalization, but we probably think about it in generic terms. And if we think back to the constraint that transitions should be faithful to content, this is a transition that's mostly going to be faithful to content, so it may be a good kind of transition to have, even though it's not logically valid. I'm thinking of this as a case where there is no further premise. It's not like secretly a case like this. You've just been set up by experience to make these kind of transitions. So the trick is to be able to harvest the benefits of these content-specific dispositions, which you've learned laboriously through lots and lots of experience, ones that go via your sensory motor resources, and maybe this might be affective and value-based resources, and ones that happen directly, while still being able to go in when necessary for these very general forms of reasoning to do, reasoning with abstract thought. And I think there are some potential models for that. So Chris Eliasmith has a semantic pointer architecture that has a relation between these kinds of things based on pointers. And Jake Quilty-Dunn, who I've worked with thinking about concepts generally, he's got a model where he thinks of concepts as pointers to bodies of information. And I mean, I should say he's working it out in a very different way than this, and in a way that's a bit antithetical to the neural network embedding, but that notion of pointers is another way of, I think, of working out this relation. So this goes to the thing that Penn and colleagues were arguing is distinctively human. I mean, whether or not we think that's right, I think they're getting onto something which is like particularly well developed in human conceptual thinking, and does account for something about the flexibility and power of our human conceptual thinking, which is that it can do both kinds of process. It can do this non-content-specific logical one on top of being able to do this one, and can move back and forth between them. So concepts are a kind of mediator between these stamped-in non-content, these stamped-in domain-specific, content-specific transitions, and this more abstract way of thinking. Now that raises a whole host of problems. On the verges here, I've been referring to the problem of what to compute with once you've got these compositional representations, and you can produce a very large, or maybe unbounded number. And then I said, look, the computational problem at decision time is very big if you have to compute over all of them, or even to work out which ones to compute with. So there are those frame problem type issues, which it seems empirically we do have solutions to, but that's another whole set of things to look at. What I'm just arguing now is that one of the powerful things about concepts is that they can be embedded in computational steps of both kinds, and they can mediate between them. I hope that will help illustrate the distinction a bit. Okay, I was going to talk about related distinctions, but I think that will take too much time. So I'm going to stop there for questions, and please do ask me about any of the related distinctions in the literature when we come to Q&A, and indeed anything else. I'm very much looking